Welcome to Assignment 1S, which is about rational functions, a new topic for us in Pre-Cal. We have two learning objectives, which is going to be two skills that you need to learn from this video. Skill number 1, can you describe the end behavior of a rational function? And skill number 2, can you describe the domain of a rational function? Keep in mind that there are two skills that are going to be on the mastery check. What does this mean? Let's say I have a rational function like the one right here. Even looking at this graph here, I can analyze the end behavior of the graph and write it in a limit notation like this. Moreover, I can describe the domain of this graph or this rational function in either set notation or interval notation. Your answers are going to be looking a lot like this. So let's start to write the notes. I'm throwing around the word rational function, but I haven't really told you what that is. Ratio is a fancy way of saying divide, okay, or fraction. A rational function is when I have a function that's defined as the fraction of two polynomials, and there's a polynomial in the numerator, which is the top, and a polynomial in the denominator, which is on bottom. Here are some examples of rational functions and how to tell that they're rational. First of all, there's that big division sign. It's a ratio of two polynomials. This one is clearly a rational function. Even this one right here is clearly a rational function because if I were to multiply out these factors, I would get polynomials both on top and bottom. And even this simple function here on the right is also a rational function because 1 is a polynomial by definition, and so is n. All right, let's do a quick service announcement. Let's go back to elementary school. You should have learned this one fact about division. It is impossible to divide by 0. No matter what happens in math, we are never allowed to divide by 0 because it means nothing, okay? Even the Desmos calculator will not allow you to divide by 0. And the answer is not 0. The answer is undefined because it does not exist. Dividing by 0 is impossible. You can divide by any other number. You can divide by 10,000. You can divide by 4. You can divide by a little decimal. It doesn't matter what you do. You're not allowed to divide by 0, okay? Just like the meme. And that leads us to example number 1, finding the domain of a rational function. Okay, remember what domain is. Domain are all of the possible x's of a function, meaning what can my x's be? And you look at the graph right here, and you notice that something happens around this area. What exactly is happening there? Well, let's find out. Well, given that service announcement, which is the key to today's assignment, the denominator can never equal 0, and therefore x cannot be a number that would cause the denominator to equal 0. So I'm going to say that 3x plus 12, whatever this calculates to be out, it better not be 0. Now let's ask ourselves, which x would cause that? And looking here at the graph, it looks like -4 is going to be the answer. Let's solve for x. I'm going to subtract 12 on both sides. We're just using normal algebraic processes. And that gives me that 3x cannot equal -12. I'm going to divide 3 on both sides. And -12 divided by 3 is -4. So now that we know that x cannot equal -4, it explains why my graph skips -4 and there's a major change that occurs there. So how do we notice this? We're going to start drawing what are known as vertical asymptotes. These are lines that we like to do as a dash, and these are lines where our function starts to hug them, meaning the function gets closer and closer and closer to those lines, but they never, 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 never touch those lines. So this vertical line, which is called our vertical asymptote, can be described by the formula x equals -4, and that is our vertical asymptote. Okay, now let's go to our domain. So x cannot be -4, but x can be every other number. So in set notation, we write x is every x that is not -4. That's what the set notation means. It's actually the easier one to write. Now let's talk about the interval notation. Now that I have this asymptote, that asymptote cut my graph into a left side and a right side. On my left side, my x values go from -infinity and they go all the way up to -4. And then on the other side, we skip -4, and we go from -4 to infinity. So my graph was cut into two parts by that asymptote. Therefore, my domain is the union of the interval that describes the left of the asymptote and the interval that describes the right of the asymptote. So left interval is from -infinity to -4. There's a parentheses here in union with parentheses -4 all the way to infinity. And remember, because -4 is not an allowable number, we are not allowed to equal -4. We cannot include -4 in the domain. Let's do example number 2. In this example, we're given a formula, but there's no graph, and we're not allowed to use the calculator. Well, what you're going to learn is figuring out the domain and the asymptotes and all of that very good stuff is best done when you can convert a polynomial into factored form. And you do that by factoring each polynomial. The top part's already factored, and the bottom part I can factor as x minus 6 times x plus 4. Now, rational functions are great until the denominator equals 0, and then they're undefined. And therefore, the denominator cannot equal 0. So I'm going to write that expression out. I'm going to ask myself, which x's are forbidden? What are the naughty x's that would cause this expression to equal 0? Well, factored form helps us figure that out really quickly. I know that x cannot be 6 because that would create a 6 minus 6. And I know that x can't be -4 because that would cancel out that 4. So I have two forbidden x's. I don't know what the graph looks like. I just know that at 6 and -4, there's either an asymptote or somewhere where the function is not defined. And so the domain is simple to write in set notation. Every x such that x does not equal -4 or x equals 6. And with interval, I have 3 intervals. I have the interval to the left of this asymptote, the interval between the asymptotes, and the interval to the right. So I'm actually have 3 intervals, okay? This is how I would write it out. From -infinity to -4, from -4 to 6, and from 6 to infinity. The important thing there is that -4 and 6 are not included. We are leaving them out, and therefore we have to use parentheses to exclude them from the interval. In this example, we have a pure graph, and we're asked to find the domain. Well, I'm going to look for asymptotes. I'm going to look for skips in the line. Go ahead and take a look and let me know what you think the x values are that are forbidden. Well, I'm noticing that there are 2 vertical asymptotes, one at x equals -2 and one at 5. So I'm going to just draw them with dashed lines, and you can see that they are indeed asymptotes because the lines are hugging them when you go toward the line. And so in set notation, I now know that x cannot equal -2 because the graph skipped it, or 5. And in interval notation, there are 3 intervals. And remember, we always write our intervals from left to right, from -infinity to -2, from -2 to 5, and from 5 to infinity. And since -2 and 5 are not included on the domain, that's why they are in parentheses. Let's do a review of limit notation. This is going to help us figure out what's happening on the M behavior. So to write a limit notation, you got to write LIM. You have to write below it x approaches, and there's going to be some number here. You write the function, you put an equal sign, and you got to write what the y value approaches. When you read a limit, you can just interpret it like an English sentence. As my x value approaches this number, my y value approaches that number. On the AP exam, if you don't write limit notations with accuracy, they won't count them. When we did polynomials, y'all were very good at doing the limit notation for the end behavior. Take a look at this function right here. I'm noticing that as my graph goes to the right, meaning as my x's get larger and larger, my line is going up at an angle, and it's not hugging anything. It's not hugging a horizontal asymptote. That arrow is going to go up and up and up forever and ever. So my end behavior for the right side of the graph is that as x approaches infinity, so does my y value. As x approaches infinity, meaning it's going to the right, the y value also approaches infinity. And looking at the other side of the graph, as my x's get more and more negative, and as they approach negative infinity, my line here has an arrow showing me that this line is going to go down forever and ever. So therefore, as x approaches negative infinity, my y value also approaches negative infinity. This is a lot like those odd polynomials. All right, let's do example number 5. So in this case, we only have a formula, we don't have a graph. The best way to approach that is to plug bigger and bigger numbers into x to see what happens when x gets bigger, heading toward infinity, and to do the same thing in the negative direction. And the best way to do that is with a table. So in Desmos Graphing Calculator, you can type in function g as such. And we're going to create a table by clicking on the gear and then clicking on the Create Table option. And here, this is where you can put and change these numbers. 0, 10, 100, 1,000, 10,000. All I'm doing is making my x value get larger and larger. Plugging that into this table, I'm noticing that my number starts to get smaller and smaller. It gets a smaller and smaller decimal. Here it is 4 thousandths. Here it's 4 10,000ths. The larger this number was getting, the closer this number was getting to 0. When I go back into Desmos and put the negative values, meaning I'm approaching negative infinity, the same thing's happening. My decimal gets smaller and smaller. Even this last one here in scientific notation, you notice that we have a -4 exponent, which means it's a really small number. So plugging those numbers in, I see that my g value is getting smaller and smaller, 4 thousandths, 4 10,000ths. The larger this number gets, the smaller that number gets. It's heading towards 0. So let's write that out as limits. As x approaches infinity, meaning it's increasing without bound, or as x approaches negative infinity, meaning it's decreasing without bound, my y value approaches and gets closer and closer to the number 0. The larger the x in terms of its value causes my g function to be 0. So as x approaches negative infinity or as x approaches infinity, my g function is approaching 0. All right, let's do a graph here. Now you're good at probably identifying the vertical asymptotes. There's also a horizontal asymptote, and you can see that this function right here is starting to hug y equals -2, meaning I can draw a dotted line that's at y equals -2, and I see my function is hugging that line. So that tells me about the end behavior. The arrow is not pointing up or down or at an angle. The arrow is getting flatter and flatter on that line. So as my x approaches the right of the graph, meaning as my x gets larger and larger, my function just starts to come closer to -2. And then on the left side, as my x values go to negative infinity, my y value is getting closer and closer to -2. So I can write that out as limits on both sides. As x increases without bound, the y value gets closer and closer to -2, and as my x decreases without bound, the y value gets closer and closer to -2. I do have a mistake. I just noticed it right here. Since they told me that this is a graph of f, I should have wrote f here, not g.